Hello, I welcome you all in this presentation on the ultrasonic welding process related to the subject joining technologies for the metal. This ultrasonic welding process is one of the solid state joining process, where very less heat is generated at the interface by friction. And another important thing, there is no melting or fusion, there is no use of filler. So, the melting surfaces are brought together in metal to metal contact, and then using the vibratory energy, ultrasonic vibratory energy, the joint is made through the localized plastic deformation at the interface. So, very less heat is generated, which at the most comes out to be like say 35 to 50% of the, like say the temperature rise due to the heat generation is the temperature of melting point in absolute scale. So, 35 to 50% of the melting point temperature in Kelvin of the metal, that is the maximum temperature rise due to the frictional heat generated in course of the welding. And this heat helps to soften the metal, facilitate the plastic flow of the metal at the interface. So, sequentially we will see now that what kind of system is used here. Let us say this is the base and the component to be joined is placed over the base. The base will support the workpiece or the workpieces and the load which is applied. So, loading or the clamping force is supported by the base. Another component to be joined in very clean condition is placed over it like this. So, there is a direct metal to metal contact between the two components. This is part 1 to be joined with the part 2 say, and then over this one member is brought in contact with the surface of the one of the component which is placed at the top. This is a tip of the sonotrode. This transfers the vibratory energy to the plates or the sheets being joined, and this is done with the help of one arrangement wherein we will see that this is the transducer which will be supplying the ultrasonic vibrations like this. This component is vertical and then applied load. So, here the load is applied which will apply the necessary clamping force, and this one is called reed. Through the reed the load is applied onto the workpiece, and this transducer will be supplying the necessary vibratory energy. So, it will be at a very high frequency. So, this in turn will be causing the lateral movement at the tip. So, basically the force is applied through the reed, and the you can say the shear force is applied through these vibrations at very high frequency. So, the tip basically applies both a combination of the compressive force, clamping force, and the shear force. So, shear force, the clamping force is static in nature, while the shear force is dynamic, acting literally and acting at a very high frequency. So, when there is a direct metal to metal contact, like say this is the real surface of the upper component and the real surface of the lower component having the contact at peaks and valleys under the constant static load and the lateral shear force. Initially the oxides, impurities, all these are flushed out or removed from the interface. So, these impurities are removed and direct metal to metal contact is established in the initial stage under the effect of the static clamping force and the vibratory shear forces. Once this contact is established, metal to metal contact is established, actual contact area starts to grow, and this growth is facilitated by elastic plastic flow of the metal at the interface. So, as the process continues, elastic plastic flow at the interface will continue to increase, and this in turn will keep on increasing the direct metal to metal contact area, and subsequently we will see that the contact between the two pieces to be joined is perfect, and under this condition what we will see? We will see that due to the elastic plastic flow of the material, especially at the interface, the so what are the things involved? The friction and elastic plastic flow. All these things will generate enough heat. So, heat generation will cause the temperature rise 0.3 to 0.5 times of the melting point of the metal in Kelvin, right. So, this increase in temperature is high enough to cause the recrystallization and the formation of the new grain, and these things actually facilitate the refinement of the grains at the interface one, and the second is cold or work hardening due to the plastic flow of the metal. Work hardening, although this is very mild or the moderate. So, the material which is formed at the interface is moderately cold worked and the refined. Why? Due to the elastic plastic flow as well as the frictional heat generated causes the enough temperature rise for the recrystallization to take place. So, if we measure the hardness at the interface, we may find that if this is the interface, then on approaching towards the interface we may find increase in bit hardness, and this increase in hardness is attributed to the moderate work hardening which is taking place due to the elastic plastic flow of the material at the interface, and then additionally the grain refinement of the material at the interface due to the continuous deformation in both the direction of the material in course of the ultrasonic welding process. So, in this case what we have seen, we are applying the static load which will be basically holding the workpieces to be joined, and then lateral force, lateral shear force which will be applied through the in form of vibratory energy through the transducers. With this combination of the two actually facilitates the very elastic plastic flow, very dynamic conditions at the interface, and facilitate the elastic plastic flow of the material at the interface, and that in turn helps in development of the joint at the interface. So, keeping this principle in mind, if we see that no external heat was supplied and only so we did not supply heat from the outside, and despite of this without any supply of heat, only the frictional heat caused enough temperature rise, like say 35 to 50% of the melting point of the metal in Kelvin scale, which is found to be enough for recrystallization of the material, and the plastic deformation coupled with the recrystallization results in the refinement of the grain structure also. So, since there has been no melting, so no cast structure, no heat, and the heat being generated at a very small area at the interface, and therefore the issues related with the heat are extremely limited. So, no heat related issues in case of the ultrasonic welding, and because of this we will see, since there is no melting, no cast structure, and the heat being generated over a very small volume of the metal. So, what we will see, very less HZ, very reduced residual stresses, and any dissimilar systems, dissimilar metals which are metallurgically incompatible metals can be joined by this process. Okay. So, these are some of the benefits. Additionally, due to the inherent nature of the process itself. Now, we will see the things which actually matter in development of the sound and perfect weld joint. So, for that what we need to see, like this is the upper component, and this is the sonotrude, transferring the vibratory energy, supplying the lateral shear force through the vibrations, and the static clamping force, and this is the another member with which it is to be joined. So, part A and the part B. So, how much the vibratory energy is to be supplied? There are some aspects like how much vibratory energy is to be supplied. This is one thing, and the second is how much force is to be applied for development of the sound weld joint. So, what is important here? The kind of surface conditions, like surface roughness, presence of the impurities, hardness of the material. So, the factors that affect these two, vibratory energy and the clamping force which is to be applied, is influenced by the thickness of the sheets to be joined. This is one, thickness of the sheets to be joined, then hardness of the material. Then we will see that yield strength and the percentage elongation also to some extent determine the plastic flow behavior of the material at the interface during the process. So, these factors also affect the amount of energy that it will take before development of the sound weld joint, apart from the presence of the impurities and the oxides, etc. So, since the thickness and the factor that is governing the ability for the plastic flow influence the success of the process significantly, and that is why these two parameters significantly determine the energy which is required for development of the ultrasonic joints, and which is given by, say, the vibratory energy need to be supplied, say, in joules, is found a function of the K multiplied by H into T raised to the power 3 by 2. So, this is the energy in joules, or K is constant for welding system being used for development of the weld joint. H is the Vickers hardness of the material which is being joined. So, higher is the hard, so this Vickers hardness number will come, higher is the hardness, greater will be the higher will be the resistance for the plastic flow, and so greater will be the energy it will take for development of the joint. And similarly the thickness T, thickness of the sheets being joined in mm. So, the thicker is the plate, greater will be the energy requirement for development of the weld joint, because this need to be transferred across to the interface, and then so the thickness of this top sheet will definitely be mattering here, definitely be important. So, greater the thickness of this plate, greater will be the energy requirement to be welded, and similarly higher is the yield strength, higher is the hardness, lower is the ductility, greater will be the requirement of the energy for developing the sound weld joint. So, considering this point, the materials having low sigma y, low hardness, they will be easier to be welded, and similarly less in thickness, they will be easier to be welded. So, thin sheets and soft metals can be easily ultrasonically welded as compared to the harder high strength materials of the heavier sections due to the energy requirement, and it is the capacity of the ultrasonic welding systems that actually limits the maximum thickness which can be welded using this process, since not very high energy ultrasonic welding systems are available. So, the process is basically limited to the thin sheets or very thin gauge sheets, and therefore, what we will see limitation wise, as far as the limitation, the process is limited to very thin sheets, and this limitation comes primarily from the non-availability of high energy ultrasonic welding systems. So, if we have high energy ultrasonic welding systems, then definitely it is possible to join even the sheets of the greater thicknesses. Another one is that this is limited for the lap joint configurations only. In other configurations, joints are not so easily possible. So, therefore, these are the two major things can say associated with these processes in form of the limitations. Now, the kind of joints which can be made using the ultrasonic welding process, if you have to see, the ultrasonic welding process is very common that spot joints are made, wherein one sheet is placed over the another and one spot kind of joint is made at the interface. So, section will be circular in this case, and its area will determine the shear strength load carrying capacity of the joint. So, this is most common form which we can say as variants of the ultrasonic welding process. One is spot joint, another is you can say line ultrasonic joint, where primarily if you will see this in top view this is the this is the upper plate and this is the lower plate, like this. Two have been joined, and then in this case joint is made at the interface along particular line like this only. So, in this case ultrasonically welded joints like 3 joints, but in form of the line. So, of course, we have to use the sonotrode tip according to the shape which is desired. It can be of any other particular contour also, like it can be triangular, it can be oval, or it can be circular shape like a spot weld. So, in that case like say here this is the top seat and this is the bottom one, and if you want to make the joint of a particular configuration, in that case the sonotrode tip is to be made according to the shape desired, like say in that case weld line will be made according to the geometry of the sonotrode tip shape, and this will be the kind of the joint along which it will be made. So, it can, this will be the like contour ultrasonic weld joints, where the joint geometry will be governed by the geometry of the ultrasonic sonotrode tip. So, these are the different variants, and as it has been said that the process is limited to the thin sheets. Now, we will see some other details and few examples of the typical situations where ultrasonic weld joints are used. So, we will quickly go through the figures and specific diagrams. This is the dead weight or the force through which it is mass or the force through which it is applied through the reed, and then the wedge will be supplying the vibratory energy through the transducer to the sonotrode tip, and here we have the seats to be joined, and this is the base or the anvil which will be providing the support to the clamping force, as well as the force which is being generated in course of the welding. The very localized application of high frequency vibratory energy under pressure and metallurgical bond at the interface is created, like this is sonotrode tip, static force and vibratory energy facilitates the deformation at the interface, and that helps in development of the weld joint. Ultrasonic vibrations are transmitted through the transducers. Transducer transmits the vibrations through a coupling system, and clamping force is applied through the reed. These are the various process variants, as I have said. It may be a spot, a ring, line, continuous seam, wherein the rotating disc shaped sonotrode tape is used, or the closed loop weld, like I have explained. According to the requirement, the sonotrode tip is shaped for circular, square or oval shape. So, sonotrode tip in that case made hollow, and the tip is contoured to the shape desired. The different variables that affect the success of the process, one is clamping force and oscillating shear force, and under the process conditions due to the friction and deformation heat is generated. So, the heat generation is moderate, and these factors means the clamping force and oscillating force magnitude is influenced by, means their selection depends on thickness of the sheet to be welded, hardness of the material and yield strength, and the surface conditions, of course. So, the combined clamping and oscillating force causes the elastic plastic deformation at the interface. This is what we can see, the clamping force and the ultrasonic vibrations appearing in form of literal shear force, and the two sheets are welded and the samples are supported over the anvil. So, in course of the process, what happens? Initially the contact at the interface breaks the surface films and oxides, disperses them, and metal to metal contact is established. Gradually the elastic plastic flow of the material at the interface continues, which in turn grows the size of the weld being made, and in this process itself diffusion at the interface takes place, and at the same time frictional heat causes enough rise in temperature for recrystallization to take place, that in turn defines the grain structure. As I have said, the success of the process depends that how effectively energy we can supply, and how much energy we need to supply. So, energy to be supplied, electrical energy to be supplied in course of the process is found a function of the hardness of the material, viscous hardness, and the thickness T, and this will be governing the kind of how effectively the sound weld joint will be made. So, as per the thickness and the hardness of the material, we need to supply the different amount of the energies for ultrasonic welding process. Advantage of the process, as I have said, very less heat is generated, that too with the friction only. Therefore, heat effector zone is very limited, residual resistors are very limited, no melting. So, there is no nugget or intermetallic formation possibility. We can weld thin to thick sections, but normally thin sections are welded, thick sections are difficult due to the availability of the high energy ultrasonic welding systems. Variety of dissimilar metal systems can be welded, and these weldments can be made even through the thickness. So, means if the base metal is coated, then through the coatings also the joint can be made by the ultrasonic welding process. So, the amount of energies which are required for welding aluminum and copper, they are much less as compared to that is required for resistance spot welding. Similarly, the weld cycle time is very short, pressures which are applied are much lower as compared to those which are used in case of the resistance spot welding process for joining of aluminum, copper, and other high conductivity, high thermal conductivity metals. So, thickness deformation in this case is also very limited as compared to the cold welding process. Limitation wise, as I have already talked, the process is limited to the thin gauges because of the power limitations of the ultrasonic welding equipments which are available, and the process is limited to the lab joints only. Applications, the assembly of electronic components, because the process is very light, it can be used mainly for the thin gauges, and then electrical connections, broken aluminum foil, packaging applications wherever. So, thin sections need to be joined of very delicate materials, this process is used very effectively, and in structural welding also, like in helicopter access doors, this process is effectively used. So, now here I will summarize this presentation. In this presentation I have talked the basic principle of the ultrasonic welding process, different factors that affect the soundness of the success of the process, and the process advantages and the limitations, besides the areas where this process can be used. Thank you for your attention.